Now, another tool that I may have mentioned, but we want to reemphasize, is if you go in your course to My Lab in Mastering, and if you go down here to, normally you're dealing with assignments, but if you go here to Mastering Course Home, click on that. Something like this will open. It's taking a moment here. Okay. And we get this. Now, one of the menu bars on the left is Multimedia Library. I'm going to click on that. And here, depending on which modules you're working on, and the one we're working on is, of course, Unit 3. And the section we're interested in particularly is Conditional and Circuits. Click on that. And then we want to look at media types. And of course, all of these media types may be available. So I'll click Select All, and I'm going to go Find Now. Well, as I look at selected video lectures, here's the one I'm talking about, video lecture Conditional and Circuits. Now, these are what we use for our PowerPoint, and these are some other videos too. And of course, there's the textbook. This is what I use to make our lecture booklet. All right, let's click on this. Comes up a little small. We'll get an idea what it's like here. And there is a little button here to make it bigger. So now I have it full screen. Let's listen a little bit. And we'll start it. If you go into it a little further, around 10 minutes or so, it gets to the part on the circuits. I think they do a good job here.
Logic was seen in the master's thesis of Claude Shannon in 1937. Shannon showed how logic could be used to design electrical circuits. For instance, the upper left-hand picture is our simple diagram of a circuit. This one is open. And again, a circuit is either open or closed. As is in logic, a statement is either true or false. So when you have an open circuit, we take that as being a false statement. If the circuit is closed, then we would consider that a true statement. So let's apply that to logic. Let's look at the next diagram. We have a series circuit. So in order for electricity to flow the whole way through this, they would both need to be closed, saying that they would both need to be true. So the diagram that you're seeing here with the two circuits, one right after the other, would be an instance of an AND statement. So P and Q could be, this diagram could be used for a P and Q situation. Now look at the parallel circuit. Imagine electricity entering here and leaving here. Well, in order for that to happen, only one of the two have to be closed. The other one could be open. So this is the instance of an OR statement. P or Q. How about the third statement, or the third diagram? We have P and, left parenthesis, Q or R, meaning the electricity must pass through P, and then it must pass through either Q or R for it to leave the other side. The next diagram, we could write this one as P or Q, P or Q first, then and, not Q. We have the next diagram. It's got to do one or the other, so it's either going to go this way or it could go this way. So we could write this as P and Q, that's the top one, or the bottom one, P and R. And finally, the last one, again, you can see this is an OR situation. It's a parallel circuit. So we could either do not P or Q and not R. In a previous section, you learned what it meant for two statements to be logically equivalent. And here is simply a review from information from earlier sections. You may need this information to change a problem from one form into an equivalent another form.
And we're back to this page. That last reference, of course, was using De Morgan's laws to write equivalent statements. Now, this could become quite tedious. We're not going to go into it that much, but basically what was shown on that circuit chart that we just reviewed by the author is where we're going, keeping in mind that if it's open and they're calling that P, then closed would be negate P. That is the opposite. So again, so much depends on definitions. All right, we'll keep this around 7 or 8 minutes or so.